everyone. Today I'm going to be talking about the Fibonacci sequence and writing up an implementation for it. It almost seems like it's a rite of passage for people who do sorts of programming videos or tutorials. So to start off in talking about the Fibonacci sequence, I wanted to hop over to OEIS, the Online Encyclopedia of Integer Sequences, and point out an interesting part of the history of the Fibonacci sequence. You can see here this first comment is that before Fibonacci wrote his work, Indian scholars had already talked about the Fibonacci sequence in the context of pattern making. So alternatively, you can call the Fibonacci sequence the Gopala Hemachandra sequence. And if I'm mispronouncing that, feel free to leave a comment in the comments to tell me the correct pronunciation. If you're not familiar, here's the sequence. We start with the numbers 0, 1, and then every element in the sequence after that is the sum of the two previous elements. So the third element in the sequence is the sum of 0 and 1, which is 1. The fourth element is 2, because it's the sum of 1 and 1, and so on and so forth. 3, 5, 8, 13, 21, 34, so on and so forth. So we're going to implement this today. I have created a new directory called Fibonacci. You can see that it is empty, and we're going to open up VS Code. In VS Code, we'll go ahead and create our main.py file. And we'll implement the Fibonacci sequence iteratively, which is kind of the most intuitive way, but we'll also do a recursive implementation and add on caching after. If any of those terms don't make sense to you yet, I'll explain it as I go along. So let's go ahead and define a function called fib. We want to accept a parameter in, which is an integer, and we want to work on this. You can see that we already have a filled-in implementation from GitHub Copilot, but we're not actually going to be implementing it this way. Let's initialize an answer variable. Actually, we don't want to initialize an answer variable. I was thinking about the factorial, not the Fibonacci sequence. Let's initialize two base variables, a and b. These are our starting integers, which will correspond to 0 and 1. And then we're going to turn off GitHub Copilot to make sure that things don't get spoiled for us. And then we are going to go ahead and iterate up in total steps. So for some random variable, we don't actually care, so we're going to use an underscore to say that we don't care about the variable. For blank in range in a comma b equals b comma a plus b. So what we're doing here is we're just saying a becomes the value of what b is, right? We're shifting the values over, right? So if a and b are initially 0 and 1, we're making a the value of b, so now a is 1, and b is the value of their sum, 0 and 1. And then so on and so forth, we would have 1, and then 1 plus 1, carrying through. So we do this, and then we return either a or b. I think we'll probably need to return a. That's just to make sure that the Fibonacci sequence returns the right value for n equals 0. So let's test this out by printing out fib of 0. We should expect this to be 0 because the Fibonacci sequence is defined as 0 for 0 and 1 for 1. We can see that it is 0 for 0. Let's test fib 1, 1 for 1, 1, 2. Excellent. So let's go ahead and get an array of, say, the first 10 Fibonacci numbers, and we'll compare that to what's provided on OEIS. To get the list of Fibonacci numbers, we can say numbers equals So what this is doing is this is a list expression that calls Fibonacci of n for every integer in the range 0 to 10 where we don't include 10. If we want to include 10, we'll ask for range 0 to 11. What range does in Python is it will always give us 0 to some number n minus 1. It excludes the top number because reasons in computer science, and we can talk about that in another video. Now let's go ahead and print out numbers. And you can see we go 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. So let's hop over to OEIS. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55. Everything is looking good. Now, this might be different than the Fibonacci implementation that you often see in tutorial YouTube videos. That's because a lot of people like to use recursion to implement the Fibonacci sequence. We can see it even here. The definition of Fibonacci of n is equal to the Fibonacci of n minus 1 plus n minus 2. And we just define arbitrarily the Fibonacci of 0 to be 0 and Fibonacci of 1 to be 1. So let's go ahead and implement it this way. So we want to return Fibonacci of n minus 1 and n minus 2. Now we need to define our base case in recursion. This is very important. We always want a recursive function to return to something that we know for certain. In this specific context, the values that we know for certain are Fibonacci of 0 and Fibonacci of 1. So we'll hardcode those. And then that's our implementation. We'll go ahead and test it out. And you can see that we're producing the same values for our numbers 0 to 10. Now, this recursive implementation of Fibonacci is actually pretty inefficient, because what we do here inside this recursion, each of these functions, each will call 2 more functions themselves, and each of those will call 2 more, all the way down to 0 and 1. So what we're looking at is a exponential complexity. It actually might even be even worse, factorial complexity. Let me think for a second. It splits into 2. Yeah, I think it's an exponential complexity. That means the Fibonacci function scales approximately with 2 to the power of n, where n is your input to the Fibonacci sequence here. So let's go ahead and test this out by generating to the range 1000. And as a quick tip in Python, if you use underscore, you can separate out numbers, constants that you type into your Python programs, and it doesn't actually change how it's evaluated. It's just a useful tool for making the numbers look visually appealing. Now, when we run this, you can see that the code's not done yet, and that's because it's very expensive to calculate Fibonacci of 1000. Like I said, we're performing effectively 2 to the 1000 calculations, which, if we check out, is an absurdly high number that definitely will not be finished anytime soon. So let's cancel this. And just to show you how much faster it is with the iterative implementation, we'll run it here, and you can see we get the result practically instantly. So how can we increase the efficiency of this recursive implementation, other than just using the iterative implementation? Well, what I have in line for you is the functools built-in library in Python. And specifically, we're looking at the cache function here, which is actually the first one. So what this does, yes, it memorializes. Basically, it's just saving the results of a previous function call. Because if you notice, when we call Fibonacci of n minus 1 and Fibonacci of n minus 2, when Fibonacci of n minus 1, like when we're inside that function, it itself is going to call its n minus 1, which so happens to be exactly the same as n minus 2. So we're redoing a lot of work. And we can save all of this work essentially for free by using the Python built-in cache function. So we're going to import it. And all we have to do is add a decorator on top of the function, like so. And then let's go ahead and try running the Fibonacci function again. And you can see that we get it essentially instantly. And this is because it saves all this work that's being redone and doesn't make you redo it because it knows immediately. So when we go all the way down to Fibonacci of 0 and 1, it then builds it back up from the bottom to the top. There are 2 different types of recursion, bottom up and top down. That's out of the scope of this video. But if you are interested in learning more about recursion, I highly recommend Googling top-down recursion versus bottom-up recursion, and learn about these base principles that drive all sorts of recursive programming. And that's it for this video. Thank you for checking in, and I hope to see you soon.